Welcome to the Quarkside Quantum Physics Podcast, an exploration of the fundamental structure of reality, where quantum laws govern matter, energy, and information. Here, uncertainty is a feature, not a flaw, and understanding begins at the smallest scales.
Welcome back to The Deep Dive. Today is Wednesday, February 11th, 2026. And I have to ask you, does it feel like we're living in the future yet?
You know, it's getting there.
Oh.
In some ways, yes. In other ways, not so much.
Right. It's getting there slowly. But the topic we're diving into today, this is the one that I really think finally pushes us over that edge from what we'd call modern into something genuinely futuristic.
I'd agree with that.
We've been looking at a whole stack of research, a ton of articles and analysis, all on quantum technology. And I have to be completely honest with you, and with everyone listening, when I first saw this topic in the queue, I kind of groaned.
Oh, really?
A groan. Why is that?
I did. Because quantum, to me, it usually means one of two things. Either, one, it's this completely incomprehensible math that just makes my head hurt thinking about it.
Fair enough.
Or two, it's just this lazy plot device in a superhero movie, you know? Mm-hmm. They just say the word quantum to fix whatever plot hole they've written themselves into.
Right. The quantum realm solves everything. Exactly. It feels distant. It feels like something that's happening in a super-cooled basement at some university that has absolutely zero effect on my actual life.
And that's the common perception.
Yeah,
for the last, 20 or 30 years, that was a pretty fair assessment. It really was just theoretical physics.
But the sources we're looking at today, they're arguing the complete opposite.
The polar opposite. The core idea here isn't about some abstract discovery.
No. The headline of this research isn't "Scientists find a new particle." The headline is, and this is what grabbed me, "The successor to electricity is here." And that made me sit up and pay attention.
It should. That is, I think, the perfect analogy to start with. Just think about the world in, say, 1870.
Okay.
You had steam engines, you had gas lamps. It was a functional world, an industrial world. People got by just fine. But then electricity comes along and scales up, and suddenly you don't just have a better gas lamp.
Right, you have something totally new.
You have refrigerators, you have radio, television, the internet, MRIs in hospitals. Electricity didn't just improve things by 10 or 20%. It completely rewired the fundamental reality of how we live our lives.
And the central claim in all this material is that quantum tech is that same level of massive shift. It's not just a faster computer, but a totally different kind of tool.
Exactly. A different kind of tool for a different kind of problem. And we're not talking about something 50 years from now. We're talking about a transition that is gaining real, tangible traction right now in 2026.
So our mission today is to strip away all the chalkboard physics. I really don't want to hear about Schrodinger's cat unless that cat is somehow going to fix my Wi-Fi or, cure a disease.
We could do that. The goal is to focus on the practical applications.
We want to know, how does this change the daily life of the person listening to this right now? What is the so what of quantum mechanics?
And there's a lot to cover.
We've broken this deep dive down into a few key areas to make sense of it all. We're going to start with the most personal, your physical body and your healthcare. Then we'll zoom out to the physical world, so how we move around and how we make things.
Transportation, manufacturing, that sort of thing.
Exactly. Then we'll go even bigger to the planetary scale energy, agriculture, the environment, and finally we'll end with the digital world AI, your money, your security.
It's a pretty comprehensive roadmap. It touches almost every part of modern life.
It really does. So let's start with section 1, the quantum body. Healthcare and medicine. Now, the sources, they kick this off with a pretty grim reality check about modern medicine. We like to think we're so advanced, we have robotic surgery, we have telemedicine.
We have amazing tools.
But they describe our current method of drug discovery as, and I'm quoting here, throwing darts in the dark. Is it really that bad?
It's surprisingly inefficient.
Yeah.
And to really get why quantum changes this, we have to understand why it's so hard right now. So here's the reality. If you have a disease, let's say it's a new virus or a very specific type of cancer, and you want to find a molecule that will cure it, you are basically looking for a perfect lock and key fit.
Okay, lock and key. That's simple enough concept. I have a key. I need to find the one lock it opens.
Conceptually, yes. But now imagine that the lock is constantly wiggling, it's vibrating, changing its shape just slightly. And now imagine your pile of keys isn't a handful, it's the size of Mount Everest.
Okay, that definitely complicates things. A lot.
The number of possible molecular combinations that you could theoretically create it's astronomical. One of the papers we looked at estimated it to be more than the number of atoms in the known universe.
Wow. Okay, so we obviously can't test them all physically. That would take forever, literally forever.
Right. So what we do now is chemists use their intuition, their experience, and classical supercomputers, the best computers we have today, to try and narrow down that pile of keys.
They make an educated guess.
A very educated guess.
Yeah.
But here's the problem. Classical computers are binary. They speak in ones and zeros. They are fundamentally linear. And they really struggle to simulate nature because nature isn't binary. Nature is quantum.
Okay, explain that distinction for me. Why does a 1 and 0 computer fail when it comes to biology?
Because molecules don't just sit still. They vibrate. They interact with each other. They exist in multiple energy states all at the same time. So when a classical computer tries to model something really complex, like a protein folding, which is the key to how a drug actually interacts with your body, it has to make approximations.
It has to cut corners.
It has to cut corners because the math is simply too hard for it. A classical supercomputer would take, I think the estimate was thousands of years, to perfectly simulate one complex chemical reaction.
So it's giving you a fuzzy, out-of-focus picture of the lock.
That's a perfect way to put it. So based on that fuzzy picture, a drug company synthesizes, say, 1,000 potential drug candidates, and they test them in a lab, in a petri dish, then in animals, then in humans, and 999 of them fail.
And that's where the time and money goes.
Exactly. This is why drug discovery takes 10 to 15 years and costs billions of dollars. You are paying for all the failure. You are physically testing thousands of wrong answers because you just couldn't calculate the right one from the start.
Okay, so enter the quantum computer.
Right. The quantum computer doesn't operate on bits, which are either on or off, a 1 or a 0. It operates on qubits. And a qubit, because of a principle called superposition, can represent multiple states simultaneously. It could be a 1, a 0, and everything in between, all at the same time.
Okay, give me the analogy. I need an analogy here. How does superposition help me find the right key for my wiggling lock?
Think of a massive, complicated maze. A classical computer is like a mouse running through that maze. It runs down one path, hits a dead end, turns all the way back and tries a new path. That hits another wall, turns back. It has to try every single path, one by one, until it finds the exit.
Slow. Painful. Inefficient.
Very. A quantum computer, on the other hand, is like having a bird's eye view of the entire maze at once. It can survey all possible paths simultaneously. It's not guessing sequentially. It calculates the optimal path by considering all possibilities at the same time.
So in the drug discovery context, it's looking at all those billions of molecular combinations at the same time.
It's more than that. It's actually running the code of nature. It creates a perfect digital twin of the disease of the protein. So instead of mixing chemicals in a beaker to see what happens, you just run the simulation. You can test 10,000, 100,000, a million potential drugs in silico inside the computer chip in a matter of days or weeks.
So we are moving from a system of trial and error to a system of simulation and selection.
Precisely. The sources all point to this incredible timeline shift from years to weeks. Imagine another pandemic scenario.
Let's not, but okay, for the sake of the argument.
In 2020, getting a vaccine developed and tested in under a year was considered an absolute miracle of modern science. And it was. It was the fastest we'd ever done it.
Right.
With a mature quantum simulation platform, you could theoretically identify a viable molecular candidate in a matter of days. You're not guessing anymore. You have calculated the solution based on the fundamental physics of the virus itself.
That completely changes the economics of medicine. I mean, if it costs $1 billion in 10 years to make a drug, that pill is going to cost you $500. But if it costs $1 million because you didn't have to run 10 years of failed lab tests.
The pill becomes accessible to everyone. The cost plummets. But the sources go even deeper than just making things cheaper and faster. They talk about this concept of N1 medicine.
N1, so a sample size of one person.
You. Just you.
Okay, because right now, medicine is basically N everyone. If I have high blood pressure, I get the same lisinopril prescription that my neighbor gets, that my grandfather gets.
And for some people, that works great. It's a lifesaver. For others, it does nothing at all. And for a third group, it might cause a severe, dangerous reaction. Why?
Because our bodies are different.
Because your biology is chemically unique.
Yeah.
Your specific DNA, your gut microbiome, the way your proteins are structured. Currently, we can't design a drug just for you because we simply don't have the computing power to model your specific DNA against that drug. It's just way too much data.
But with a quantum system.
You can.
Mm-hmm.
You can model the interaction of a potential treatment with your specific genetic markers. This is the absolute holy grail for diseases like cancer or Alzheimer's or Parkinson's.
Because something like cancer isn't just one single disease, is it?
Not at all. It's thousands of different diseases that we just group under one name. My lung cancer might be genetically completely different from your lung cancer. So treating them both with the same blunt instrument, the same chemo bomb, is incredibly inefficient and damaging.
It's a shotgun approach when you need a sniper rifle.
Exactly. Quantum technology allows for the design of a molecule that is engineered to target only the mutated cells in your body, leaving all the healthy ones completely untouched.
That stops being medicine in the way we think of it and starts to feel more like personalized bioengineering.
It effectively is. And this leads directly to the prevention aspect that the sources really emphasize.
Yeah, this part of it just blew my mind. They call it the check engine light concept for the human body.
Right now, we practice sick care, not healthcare. You feel a lump or you start coughing up blood, and then you go to the doctor. By that point, the disease has often progressed significantly.
The car's already smoking and pulled over on the side of the highway.
Exactly. But if you can model your body's healthy baseline at a molecular level using these incredibly sensitive quantum diagnostic tools, you can detect the tiniest deviations long before they ever manifest as physical symptoms.
So before I even feel the lump, the system can see the molecular glitch that's going to cause it?
Before the first cell even divides incorrectly, the chemical precursors for that error are visible to the simulation. We're talking about catching a forest fire when it's just a single spark. You fix that tiny glitch, and you never actually get sick in the first place.
It's incredible to think about. But I have to play devil's advocate for a second. This sounds unbelievably expensive. Is this going to be a technology for billionaires, or is this something that could actually be for everyone?
That's the classic technology adoption curve question, right? The very first mobile phone in the 80s cost $4,000, and it was the size of a brick.
And did one thing, make calls.
Right. And now they're completely ubiquitous and orders of magnitude more powerful than the supercomputer that sent Apollo to the moon. The initial processing power, building the quantum computer itself, that's the expensive part. But once the models are built, the cost of running another simulation for another person drops dramatically.
So the cost is in the setup, not the operation.
Exactly. And the argument in the source material is that this eventually becomes the standard of care because it's actually cheaper for the insurance companies and the healthcare systems than paying for 10 years of failed chemotherapy and hospital stays.
That's a cynical but probably very accurate way to look at it. Economic efficiency drives adoption. If it saves the system money in the long run, the system will adopt it.
It always does.
Okay, so that's the body. We've fixed drug discovery, we're simulating cures, we're preventing diseases, but we also have to live in the physical world. We have to drive to work, we have to ship goods, we have to buy things. And the sources make a pivot here that I found really, really interesting.
So transportation and manufacturing.
Right. And believe it or not, the same kind of math that helps cure cancer is surprisingly similar to the math that delivers your Amazon package.
It is. It's all about one thing: optimization.
So how do you get from simulating molecules to routing delivery trucks?
Okay, so let's talk about a classic math problem called the traveling salesman problem. It's famous in computer science. Imagine a delivery driver who has to visit 50 different houses in a city and then return to the depot. The goal is simple. Find the absolute shortest possible route.
Sounds easy enough. Just look at a map, right?
With 5 houses, it's easy. You can figure it out by hand. With 10, it gets a lot harder. With 50 houses, the number of possible routes you could take it's staggering. It's a number with 62 zeros after it.
Whoa!
Now, on top of that, add in real-world constraints. Live traffic, one-way streets, delivery time windows, fuel constraints, the capacity of the truck.
My brain hurts just thinking about that.
And now multiply that by 10,000 trucks operating in a city like New York or London every single day. That math problem is so complex that our current supercomputers, again, the classical ones, cannot solve it perfectly. They can't check every option.
So they find a good enough route.
Exactly. They use algorithms to find a good enough route. But good enough means your package still gets delivered at 8:00 p.m. instead of 2:00 p.m., or the truck sits in traffic for an extra hour burning diesel fuel.
Good enough is inefficient.
It's incredibly inefficient. It wastes time, it wastes fuel, it costs companies money, and it pollutes the air. Quantum computers, specifically a type called quantum annealers, excel at this exact type of optimization problem. They can survey that entire landscape of 62 zeros worth of possibilities all at once.
So they don't find a good enough route. They find the absolute best, most optimal route.
Yes. The sources suggest that logistics companies like UPS or FedEx could optimize their entire fleet's routes in real time, to a degree we've just never seen before. This would slash delivery costs and, maybe more importantly, slash emissions.
And if we scale that idea up from just delivery trucks to all the traffic in a city,
that's the ultimate goal. A city traffic system that isn't just running on dumb timers, but is a living, breathing, intelligent network. It knows where every car is, it knows where it wants to go, and it adjusts all the traffic lights dynamically to eliminate congestion before it even has a chance to form.
So no more sitting at a red light at 2 in the morning when there's literally nobody else on the road.
No more phantom traffic jams where everyone slows down for no apparent reason. The whole system just flows.
But there's another really important layer to transportation. It's not just about the traffic, it's the car itself. We've been promised autonomous vehicles, self-driving cars for a decade now. It's 2026, and they are around, but they aren't perfect.
They're still a bit clumsy.
Yeah, they still get confused by heavy rain or a weirdly placed construction cone. How does quantum help fix those glitches?
It comes back to processing speed and decision-making under uncertainty. An autonomous vehicle has to process a truly massive amount of data in real time. You've got cameras, LiDAR, radar, weather conditions, the road surface, plus the erratic behavior of the pedestrian on the corner who might jump into the street.
And it has to process all of that instantly.
Faster than instantly, if possible. You need to predict what's going to happen next. Current AI is very, very good, but in those weird edge cases, like a sudden blizzard that whites out the cameras or a super complex four-way intersection with a broken traffic light, it can hesitate. It has to think.
And hesitation on the road is dangerous.
Very. Quantum-powered decision-making systems can process that chaotic, real-time data with a level of accuracy and speed that current AI struggles to match. It can see more possible outcomes and choose the safest one faster. It makes the road safer for everyone because the car's reaction time is effectively zero.
But there's another piece to the whole car puzzle, right? The battery. Because everyone says go electric, but then you have range anxiety, or the battery degrades after 5 years and costs a fortune to replace.
Yes. The battery breakthrough. This ties right back to what we were just discussing in the healthcare section, molecular simulation.
Right, because at the end of the day, a battery is just chemistry. It's just ions moving from one material to another and back again.
Exactly. It's a materials science problem. Currently, finding better materials for batteries is, again, a lot of trial and error in a lab. We want batteries that can charge faster, hold more energy, last longer, and, importantly, don't rely on rare or conflict minerals.
And are cheaper. That's probably the most critical part for the EV transition.
Absolutely. So quantum computers can simulate the complex chemical reactions happening inside a battery at the subatomic level. Engineers can design new electrolytes and new electrode materials completely virtually. They can literally watch how the lithium ions move through the material and see exactly where they get stuck or cause degradation.
So they can design the perfect battery in the computer before they ever have to build a physical prototype in the factory.
Correct. The sources are all pointing to the development of faster charging, longer ranging, and much more affordable batteries. This really removes the biggest hurdles to mass electric vehicle adoption. If your car can charge in 5 minutes and go 500 miles on that charge, the internal combustion engine is officially a museum piece.
It's pretty amazing how these different fields connect. Better computing leads to better chemistry, which leads to better cars.
And it extends to all materials, not just batteries. We are talking about designing super materials from the ground up. The sources mention things like aerospace and even textiles.
I saw that. They used a phrase, atomic quality control. That sounded like a sci-fi movie title to me.
It does, but the concept is a manufacturing revolution. Imagine an airplane wing that is significantly lighter than carbon fiber, but even stronger than steel. That saves a huge amount of fuel over the life of the plane. Or think about textiles that are designed atom by atom to be completely water repellent, but also perfectly breathable.
And atomic quality control means what exactly? Are we looking at the individual atoms while we build something?
In a sense, yes. It means catching defects at the atomic level during the manufacturing process. So instead of waiting for a product to come off the assembly line and then testing it for flaws, or worse, waiting for a wing to develop a stress crack after 10 years of use, you are monitoring the assembly so precisely that you know if a structural flaw is forming before the product is even finished.
So you just don't ship bad products. You don't waste the raw materials making something that's just going to end up as junk.
Exactly. It's the ultimate form of manufacturing efficiency. Which brings us, I think, to the world itself, to the biggest systems of all.
Section 3, the planetary scale. We're talking about agriculture, energy, and the environment. And this is where the stakes get really, really high. We're not just talking about efficient traffic anymore. We're talking about how to feed 10 billion people and not completely cook the planet while we're doing it.
This is where we start to see the potential for quantum tech to address some of our most existential challenges.
Let's start with food. Farming seems pretty analog, you know? You put seeds in the dirt, you add water and sun, you wait. How does a quantum computer help a farmer in Nebraska?
It takes the idea of precision farming to an almost unbelievable extreme. Think about a huge field. It's not uniform, right? The soil moisture in the northeast corner is probably different from the southwest corner. The nitrogen levels vary. The risk of certain pests is higher near the trees.
And right now, a farmer has to make a best guess. They treat the whole field more or less the same. They spray the whole thing.
Exactly, which is wasteful and very expensive. Quantum computers can take in and analyze data from thousands of different sources simultaneously, from sensors in the soil, from weather satellites, from drone imagery, from the genetics of the seeds themselves.
All at once.
All at once. And it can create a model that tells a farmer exactly when to plant, exactly how much water to use on this specific row of corn, and exactly where to apply a tiny amount of fertilizer to maximize the yield and minimize waste.
So we stop wasting trillions of gallons of water and stop drenching our fields in chemicals they don't actually need.
Efficiency is the name of the game. But it's also about improving the crops themselves. Just like with drug discovery and designing battery materials, quantum tech allows for the deep genetic analysis and simulation of plants.
This is the next-gen crops idea.
Right, designing crops that are inherently more nutritious, or crops that are resistant to specific regional diseases, so we don't even need the pesticides in the first place. And maybe most importantly, crops that are climate adaptable.
Plants that can thrive in hotter, drier conditions.
Plants that need less water. That is going to be absolutely essential as the global climate continues to shift. The sources also made a big point about the supply chains.
Right, reducing food waste.
If the entire food supply chain is transparent and perfectly optimized, remember our delivery truck example, then you don't have literally tons of fresh produce rotting in a warehouse because of some logistical error. You get the food to where it's needed, when it's needed, while it's still fresh.
Okay, so speaking of sustainability, let's talk about energy and the environment. We already touched on batteries, but the sources go way bigger than that. They talk about saving the climate. That feels like a pretty heavy lift for a computer chip.
It is, but the technology, or at least the theory, backs it up. Start with renewable technology itself. Better solar panels.
So we're back to materials science again.
We are. It's about designing new photovoltaic materials that can convert more of the sun's light into electricity. Right now, the commercial panels on someone's roof are about 20 to 25% efficient. If quantum simulation helps us discover a new, stable, and cheap material that's 40 or 50% efficient, you've just doubled the world's solar capacity without building a single new solar farm.
That's a huge lever to pull. But the real holy grail in this section seems to be carbon capture. We hear about this idea a lot, the dream of just sucking CO2 right out of the air. But my understanding is that right now it's really expensive and energy intensive.
It is. It takes a lot of energy to grab CO2 molecules from the atmosphere. The core problem is finding the right catalyst. A material that can act like a chemical sponge, grabbing onto the CO2 efficiently without grabbing onto all the nitrogen and oxygen and everything else.
And we just haven't found the right sponge yet.
We have some, but they aren't very good. They get clogged up, they're expensive, they require a lot of energy. Quantum simulations can help us design these catalysts at a molecular level to be perfectly tuned for CO2. If we can make carbon capture viable at a global scale, and by that I mean it takes less energy to capture the carbon than we generated by burning the fossil fuels in the first place, that changes the entire climate equation.
That feels like the ultimate undo button. But even if we generate all this clean energy, we still have to move it around. The sources talk a lot about the smart grid.
The electrical grid is the ultimate balancing act. You have supply sun, wind, coal, nuclear, and you have demand. Everyone turning on their air conditioning at 5 p.m. on a hot day.
And the sun often stops shining right around the time everyone gets home from work.
Exactly. It's a fundamental mismatch. Currently, grid operators have to keep fossil fuel peaker plants idling just in case there's a sudden spike in demand. It's incredibly inefficient.
Wasted energy.
A ton of it. Quantum optimization can ensure that renewable energy is distributed perfectly and efficiently across the grid in real time. It can predict the demand spike before it happens and seamlessly move the energy from where the wind is blowing in the Midwest to where the ACs are running on the East Coast.
So the lights don't flicker and we don't have to waste energy keeping backup plants running.
It ensures grid resilience. And when you combine that with the better batteries we just talked about, solving the energy storage problem, you finally have a clear, achievable path to a fully renewable energy system.
And we'll know if all this is working because of this idea of hyper-detailed monitoring.
Quantum sensors. This is fascinating stuff. So quantum systems are by their nature incredibly sensitive to their environment. That's actually what makes them so hard to build and maintain.
It's a bug that's also a feature.
It's the ultimate feature. That sensitivity makes them perfect sensors. They can detect tiny fluctuations in magnetic fields, gravity, or chemical concentrations that are just invisible to our current technology. They can detect pollutants at concentrations we currently can't even measure.
The sources said we could monitor air quality at the neighborhood level.
Right. It's not just Chicago has bad air quality today. It's this specific block right outside this school has a spike in nitrogen oxides. Maybe there's a tiny gas leak. Maybe a nearby factory is venting something they shouldn't be. It allows for incredibly targeted intervention.
And on a macro level, this applies to monitoring the oceans and making better long-term climate predictions.
We'll stop guessing with our climate models. I mean, they're good, but they're based on approximations because the Earth's atmosphere is a chaotic, complex system. A quantum computer can actually model that chaos. We could have truly accurate, physics-based simulations of the planet's atmosphere. We would know exactly what's happening and what the real impact of our policies will be.
That's empowering, but it's also a little daunting. The sheer level of data we're talking about is immense.
It is. Which brings us right to the systems that have to manage all that data.
Section 4, the digital nervous system. We're talking finance, security, and AI. Now, this is where things get a little dystopian, maybe, or at least very high stakes.
Money and intelligence, the two things that really run the modern world.
Let's talk money first. The sources say the shift in the financial world is going to be almost instantaneous. What does that mean for my 401k?
Well, speed is currency in finance. Risk analysis, the process of figuring out if an investment is safe or if a loan is a good idea, it takes time and a lot of computing power. A quantum computer can run millions of complex market simulations in the blink of an eye. It can model how a geopolitical event in Asia, a weather pattern in South America, and a supply chain shortage in Europe will all interact to affect a specific stock price.
So the big banks and hedge funds just get even richer because they can predict the future better than anyone else.
Well, yes, that's certainly part of it, but it also helps prevent systemic collapses. If they can model the risk in the system more accurately, they might avoid making the kind of bad bets that led to the 2008-style financial crash. But for the regular person, the biggest, most immediate benefit is probably going to be in fraud detection.
Oh, I love this, because getting your credit card skimmed is the absolute worst.
Quantum systems can analyze billions of transactions in real time as they happen. They can spot a pattern that looks like fraud instantly, even if it's a brand new type of scam that no one has ever seen before. They just see the tiny anomaly in the massive data stream.
And on the flip side of that, the sources mention personal finance getting a boost.
Yeah. Imagine an AI financial advisor powered by a quantum engine that creates a completely customized investment strategy just for you. It's based on those complex market simulations, predicting outcomes with incredibly high accuracy. It would be like having a whole team of Wall Street super geniuses managing your retirement fund, but it's just software.
Sign me up for that.
Okay.
But here's where it starts to get a little scary. We have to talk about security. Because I've read the headlines, the quantum apocalypse, the end of encryption as we know it.
The double-edged sword. It's a very real concern.
Walk me through this. The sources acknowledge it openly. Quantum computers pose a massive threat to all of our current encryption methods.
Yes, here is the scary part. Almost all of the encryption that protects your bank account, your emails, your private medical records, all our government secrets, it's based on a specific kind of math problem, specifically the difficulty of factoring huge numbers.
And those problems are hard to solve.
For a classical computer, they are practically impossible to solve. It would take the most powerful supercomputer we have today 1 billion years to crack a standard encryption key. That's why we feel safe.
But for a quantum computer,
Because of that unique ability to check all the possible factors simultaneously, just like our maze analogy, a sufficiently powerful quantum computer could theoretically crack our current encryption standards very, very quickly.
How quickly are we talking?
Minutes, potentially seconds.
Right, just pause for a second. You're telling me that the same technology that lets us simulate new medicines can also crack every password, every secure transaction, every secret we have right now. That doesn't sound reassuring. That sounds like a global arms race. How do we prevent the bad guys from getting a quantum computer first?
It absolutely is an arms race, a very serious one. That is why governments and corporations are pouring billions and billions of dollars into this research. But the sword cuts both ways. The very physics that creates the threat also provides the solution. It's something called quantum key distribution, or QKD.
Okay, unpack QKD for me. How does it fix the problem it just created?
It's actually really elegant. It uses the fundamental laws of quantum physics itself to secure the data. In the quantum world, the very act of observing a particle inevitably changes that particle. You can't look at something without disturbing it.
That's the observer effect, right?
Exactly. So in a QKD system, if you're sending a secret key for your message and a hacker tries to intercept it, if they try to look at the key to copy it, the very act of them looking at it scrambles the key. It changes it.
So if a hacker even tries to look at the data basically self-destructs.
Essentially, yes, or at least it becomes corrupted in a detectable way. It immediately alerts both the sender and the intended receiver that the communication line has been tapped. It allows you to create theoretically, physically unhackable communication channels.
So we are moving from our data being very hard to hack to it being physically impossible to hack.
That's the promise. And this leads to a whole new paradigm of privacy and data security. You could share information without ever needing a trusted intermediary, like a bank or a credit card company. Your personal data is secured by the laws of physics, not just by a password that someone might guess or brute force.
That's incredibly reassuring because we are going to need that level of security if we're going to talk about the next topic, supercharging artificial intelligence.
This is the convergence that I think everyone in the tech world is watching most closely. AI is already incredibly powerful. We see it everywhere, but it's still limited by training speed and energy consumption.
The sources say that training these massive AI models could go from taking weeks to just minutes.
Think about the big AI models we have now, the ones that power chatbots and image generators. They take months to train on huge supercomputer clusters that use as much electricity as a small city. It's a massive undertaking. If you can do that same training process in minutes using quantum optimization techniques, the rate of AI improvement just skyrockets.
But it's not just about speed, is it? It's about improved capability.
Right. Quantum AI can process context and nuance in a way that classical AI struggles with. Natural language processing could become truly flawless. But the real kicker, I think, is in pattern recognition in massive, noisy scientific data sets.
Like what kind of patterns?
Like finding a subtle correlation in genomic data that points to a new cause for a disease. Or finding a strange pattern in astronomical data from a telescope that indicates a new type of celestial object. Things that humans would just miss because the pattern is too complex and hidden in too much noise.
So the AI essentially says, hey, scientists, did you notice that this specific protein always folds weirdly when the ambient temperature drops by half a degree? And we'd say, no, we completely missed that.
Exactly. It becomes a true partner in scientific discovery. It doesn't just speed up science, it makes new science possible.
It's a lot to take in. We've covered the body, the physical world, the planet, and the digital brain. But what about just living? You know, sitting on my couch, watching a movie, helping my kid with their homework.
Section 5, the human experience. We're talking education, entertainment, and the home.
Let's start with education, because if the world is changing this fast, our current school systems are already way behind. We're going to have to learn faster just to keep up with it all.
The sources describe a complete revolution in learning, centered on this idea of adaptive learning.
We've heard that buzzword before, though, personalized learning. It usually just means every kid gets an iPad app that's slightly different.
True, but quantum-level processing power could make it actually real. Imagine educational software that adapts in real time to your specific pace and your cognitive style. It monitors your responses, your eye movements, maybe even your biometric data. It knows when you're getting bored, it knows when you're confused or frustrated, and it adjusts the curriculum for you instantly.
So if I'm not getting a particular math concept, it doesn't just repeat the same explanation back to me, but louder.
No, it completely switches tactics. It tries a different analogy. It slows down and shows you a visual representation. It uses visualization.
This goes back to the power of simulation again.
Yes. Instead of just reading about molecular bonding in a chemistry textbook, you could put on a VR headset and be in a simulation, literally watching the atoms bond together. You could reach out and try to push them apart. It makes these abstract, complex subjects completely concrete and understandable.
And with that level of high-fidelity virtual reality, remote education could feel exactly like being there in person.
Access to the world's best education becomes universal. You could be sitting in a lecture hall at Oxford from your bedroom in Ohio, and the fidelity is so high thanks to quantum processing of light and sound data that your brain feels like you're actually there. It's indistinguishable from reality.
Which is a perfect segue into entertainment. Let's talk about gaming.
This is the end of the scripted, predictable NPC.
Laughs, finally. I am so tired of the guards in video games walking in the exact same circle for all eternity.
Quantum-powered AI opponents will learn and adapt to you, personally. They'll be genuinely unpredictable. There's no more finding the pattern to beat the final boss. The boss learns your pattern. If you always attack from the left, the boss will anticipate that and set a trap for you on the left.
That sounds both incredibly frustrating and incredibly fun.
And then there's the immersion factor. VR becomes indistinguishable from reality because the system can process all that complex sensory data like sound, physics, haptics in perfect real time.
The uncanny valley where things look almost real, but not quite. That just disappears.
The sources also mention something about new genres of music and art. What do they mean by that?
Creativity that's augmented by quantum AI. The AI could generate sounds and visuals and even narrative structures that we literally haven't been able to imagine before because we didn't have the computational palette to create them.
And connecting all of this together is the quantum internet.
Instantaneous, unhackable global communication. Essentially zero latency.
This is the technology that's crucial for things like remote surgery, right? Exactly. If a surgeon in Tokyo is operating on a patient in New York using a sophisticated robot, there cannot be any lag. Even a millisecond of lag between the surgeon's movement and the robot's action could be fatal. Quantum networks, through a process called entanglement, can eliminate that lag entirely.
Finally, let's bring it all home, literally. The smart home.
We all have some smart devices now. A smart speaker, a smart thermostat. But are they really smart, or are they just remote controlled?
They're totally remote controlled. I still have to tell Alexa to turn on the lights. I have to tell the thermostat that I'm feeling cold. That's not smart. That's just a voice-activated switch.
Exactly. The quantum-powered smart home is all about anticipation. It's about systems that can predict your needs before you even articulate them.
So it knows I'm cold before I even think about reaching for the thermostat.
It knows you're cold, it knows your daily schedule, it knows the price of electricity at that exact moment, and it knows the weather forecast. It intelligently adjusts the temperature, the lighting, and even the entertainment based on your established behavior patterns. It might know you had a stressful day based on your biometric data from your watch, so it dims the lights and plays some calming music without you ever asking.
That sounds lovely, but also just a little intrusive.
It's the ultimate trade-off, right? Convenience for data. But remember the security aspect we talked about. With quantum encryption, your personal data is, in theory, completely secure and private.
And the maintenance part. This one I really like. Appliances that can diagnose their own problems.
Your washing machine's internal sensors notice a tiny microscopic vibration, a tiny anomaly in the motor's operation that indicates a bearing is beginning to fail. It automatically orders the correct replacement part and schedules a repair visit for next week, long before the machine actually breaks down.
So I don't come home from work to a completely flooded laundry room.
Never again.
That is the level of convenience I am absolutely ready for.
It's all about seamless integration into your life.
So we've covered all these different sectors, but section 6 in the material is where we really tie it all together. They call it the convergence effect.
And this is probably the most important part of this whole deep dive. We've talked about these things in their own silos, cars in one box, medicine in another, banking in a third. But in reality, these technologies do not exist in a vacuum. They amplify each other in powerful ways.
The sources give this really great chain reaction example. I think we should walk through it because it really paints the complete picture.
Okay, so let's start with quantum material science. We use that to design a better battery.
Right, and that better, cheaper, longer-lasting battery makes the electric vehicle practical and affordable for everyone.
Okay, now that electric vehicle is guided by a powerful quantum AI, making it incredibly safe to operate on the roads.
While at the same time, quantum sensors are monitoring the environmental impact of that vehicle and optimizing the traffic flow in the entire city to reduce congestion.
And the entire network, the car, the electrical grid it charges from, the city's traffic sensors, your bank account that's paying for the charge, is all communicating on a global network that's secured by quantum cryptography.
The web, it's a complete ecosystem. You can't pull on one string without the whole thing moving.
The result is a world where technology integrates seamlessly and almost invisibly with human needs and with environmental sustainability. It's not man versus machine, it's a synthesis.
It sounds almost utopian, which always makes me skeptical, but the internal logic holds up. If you can solve the optimization problem, you solve the waste problem. If you can solve the simulation problem, you solve the material science problem.
It is logical. It's
Yeah.
really the natural evolution of human toolmaking. We went from stone axes to steam engines to silicon chips, and now to quantum processors. Each step allows us to manipulate and understand our reality at a deeper, more fundamental level.
Which brings us to the outro. We have to address the timeline. Because I want all this stuff now, but I know I can't have it all tomorrow.
The sources are pretty honest about the uncertainty here. Some of these changes, like better optimization in logistics and finance, and some early-stage drug discovery, are really just a few years away, maybe 3 to 5 years. We're already seeing the pilot projects for these now.
But the full-blown quantum internet, the smart home that reads my mind.
That could easily be decades away. Scaling these systems is incredibly difficult. Qubits are notoriously fragile and hard to control, but the conclusion in all the material is crystal clear.
The direction of travel is inevitable. The sources argue that we are in the middle of a fundamental shift from computational power to simulation power.
Explain that distinction one more time for us, because that really is the key takeaway from all of this.
Right. Computational power is about doing math really, really fast. It's a super-powered calculator. Simulation power is the ability to create a perfect digital twin of nature itself, to copy the source code of reality, the atoms, the forces, the biological interactions, and run it inside a machine. That is a fundamental, profound shift in what human beings are capable of doing.
It's a shift from just observing the world to being able to accurately remodel it.
Which leads us directly to our final provocative thought for you to chew on.
We talked about perfect simulation. We talked about the smart home, knowing what you want before you even ask for it.
Right.
So, if quantum technology allows for a perfect simulation of materials and biology and complex environments, at what point does that simulation become accurate enough to predict human behavior on a massive societal scale?
Oh, wow. You mean simulating us?
If the algorithm knows you better than you know yourself, if the smart home knows what you want before you even consciously realize you want it, at what point does the algorithm stop serving you and start subtly shaping what you want?
That is a terrifying and absolutely fascinating question. Are we the user of the system, or are we just another variable in the optimization problem?
If the system suggests a movie for you to watch, and you watch it and enjoy it, did you actually want to watch it? Or did the system just make you want to watch it?
I think I might need a quantum computer to figure out the answer to that one.
It's something to think about as you watch this space develop.
Indeed. We will definitely be watching it closely. Thank you for joining us on this deep dive into our quantum future. It's 2026, and it feels like things are just getting started.
See you next time.
Take care.